Time. Dude sucks. symmetrical component. What symmetrical components are? So this I need to appear here. Yeah, I am. And it's time to speak on symmetrical components. Who are they and why we need them? The problem is in our way ahead we need to deal with earthfall protections. But earthfall protection all this useless until we are acquainted with symmetrical component. Only good knowledge in zero sequence allows to analyze earthfall protection. So it's now it's a supplement lecture, symmetrical components. In theory, those who studied in our university should know it, but I see it is necessary. So, here should appear something. Who they are and why we need to become acquainted with them. Okay, let's say we have a power line. This is my power line. Insulators. Oh, insulators. Here is my wire, and here is my earth fault. Also protective. I have protective wire above. I will use symbol P for it. From left-hand truss. Current flows in the ground. I need to analyze it. And what kind of problem do I face? Each wire, there is a magnetic couplings between wires and between wires and protective wire, and also magnetic coupling to the ground current. Towers are earthy, and it is possible, sometimes it will happen, sometimes no, what we will face, part of the current will flow through protective wire. In the simplest case, only its own or self-inductance, self-resistance of the wire plus here are wire to wire. So it will be MAB, MBC, one more, MAC, plus ohm of protective wire, on inductance of protective wire, and 1, 2, 3, A to protective. Where is my phase B? B to protective, and this one will be neutral inductance, C protective. It's a very complex thing. This thing grounds, and here we'll have A, B, C source. Very complex thing. And when the dog is digging, we can conduct an actuation system describing this. It's possible, but this system will be hardly feasible. And it will produce a heavy computation job. So base idea of technique I would like to speak of is to conduct a transform, linear transform, conduct a linear transform, eliminating elements AB, AC, BC, AE, BT, CT, so on, eliminating all this resistance from the actuation resistance matrix. Idea to craft a transform, let's say x1, x2, x3, blah, 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 being some transformation matrix multiplied by xa phase, what I'm doing, xb phase, x phase. Idea is to implement a linear kind of transform, this is transform matrix, to create a new system of coordinates, to, let's say, create an image of original polyphase system, and this image should produce a special kind of actuation system. Actuation system describing, we need a system where, let's say, current is some kind of function of voltage. System state actuation, and in this system, resistance matrix should not contain non-diagonal elements. It is possible. First one developed called Fortescue transform. In the Fortescue transform, this kind of space where real physical values are, let's say, imaged, is called space of symmetrical components. physically, it can be represented with a set of symmetrical systems. So Fortescue idea is what any non-symmetric polyphase system can be substituted with m-1 symmetrical systems. They should be come all together, plus one additional so-called zero sequence system to reflect a ground current. If you have polyphase system with the m phase, there will be m-1 symmetrical polyphase system, this one, with all possible vector sequence, plus one additional zero sequence system to reflect ground current. In our case, where M is free, we have free-phase system, the Fortescue idea substitutes a real system with a set of free systems, two symmetrical, one with sequence ABC and one with the opposite phase sequence, plus additional ABC zero sequence system. It's how it's explained physically. What polyphase, unsymmetric free-phase system can be considered as a superposition or sum of free system where two are free-phase. These angles are 230 or 120 degrees. They are symmetrical free-phase systems. Plus one where all vectors are the same. It's like attaching at the, let's say, fourth place. For the first system, it will be symmetrical. Or for the second system, it's kind and
Good morning, sir.
wait. It's a free-phase generator, but it's opposite rotation direction. And a third one will be kind of single phase machine attached to the ground where all phases are linked together. It's an idea, let's say physical representation of Fortescue transform. In mass form, any value, let's say, direct, negative, and zero sequence value, any value, current, voltage, anything, can be described like 1/3 multiplied by transform matrix 1a squared, 1a squared, a 1 1 1 multiplied by A phase value, B phase value, C phase value. Here points over values denote that they are complex, and A is a rotation operator. A is a power j 2/3 p or minus half plus square root of 3 divided by 2. Multiplication by A means rotation forward. Let's say this is some kind of x. AX means rotation forward by 120 degrees. A square equals to a power minus j 2/3 p or a power j 230 degrees or minus 1/2 minus square root of 3 divided by 2. 1 second, I will. Write it. So, a square is a power minus j 2/3 p or a power j 230 degrees or minus 1/2 minus j square root of 3 divided by 2. Is a square root from minus 1. Here is basis of Fortescue transform. There are similar transforms Clark, current power, Wedgepole transforms, several no-named. They all are crafted with idea to eliminate non-diagonal elements from the line resistance matrix. Now, I can write, for example, voltage in sequence. All these are complex values. S 1/3 transform matrix, matrix sometimes named as Kierkegaard matrix, raise voltages in phase coordinates. So it will be A phase voltage, B phase voltage, and C phase voltage. Elements of this vector are complex representation of voltages. If you want the mass-based, they are results of Fourier transform for the first harmonic of the real voltage currents. This nice Fortescue transform is worthless until we got its inverse form. We need a way to obtain real currents, real voltages from symmetrical components. After Fortescue transform, we will get system. Actually, we will get three systems with absolute symmetry. But we will need an inverse transform. Basic idea what a real system is a result of this three ideal system superposition. If result of our analysis we got x of the x of the negative sequence and 0 sequence. We supplied all this to our calculus model. Result will be what kind? Y of direct sequence, Y of the negative sequence, and Y of the 0 sequence. This is our calculus. I don't know, it's computer or it may be physical model. Not important. Important what we in the space of symmetrical component real network, real faulty line will be represented as interconnection of free network. Network of direct sequence network of negative sequence and a special network of 0 sequence. They should be somehow interconnected or interlinked. Results will be current. We will get direct sequence voltage, direct sequence current, negative sequence voltage, negative sequence current, 0 sequence voltage, 0 sequence current. All this at the final stage we may want results as A, B, C in, so we may need values in phase coordinates. Original, this one, is in phase coordinates. A, B, C phase. This one are in symmetrical component space. Results will be symmetrical components, and we need what? Here should be something between symmetrical components, ideal, and real phase coordinates. Technique of symmetrical components assumes what real is a superposition of ideals. This was in a very base of technique will be extremely important concept. We can speak on superposition or real is a sum of ideal only if real network, our network, is linear. If resistance are constant and current is always proportional to voltage. We cannot use directly this technique if we account arc resistance, because arc is non-linear. If we need to account, we are forced to account non-linearity of magnetic circuit and so on. It can be worked around separating network into linear and non-linear part. We can perform solution in symmetrical components on linear part. So, network with non-linear element should be converted into multipole network, and here non-linearity should be separated. Something like this. Later, my suggestion is converted to network with controlled, say by voltage, current source as a representation of nonlinear. So separate into linear and nonlinear part. Core network represented in symmetrical component should be linear, and nonlinear element should be separated and represented as controlled resistance or, my suggestion, controlled current source. It works better from the viewpoint of feasibility. Okay, let's go forward. Let's go forward, and what's forward? What's the inversion transform? Let's say y in sequence. Why y in sequence? I need in phase coordinates. So in phase coordinates should be in this way inversion of Kierkegaard matrix multiplied by let's say y in sequence. So y of A, y of B, y of C. It's a vector in phase coordinates equals to 1, 1, 1, 1 A square A, 1 A square multiplied by direct sequence, negative sequence, and zero sequence. Result, this may be results of calculus or results obtained from sequence network. We derive electrical model in sequence coordinates from real one. Oh, more viewers. Okay, let's try to look a bit close. Let's say I have a network A, B, C phase and one point of non-symmetry where resistance of A, B, and C phase are connected. And all this is grounded through the neutral resistance. I have A phase voltage, B phase voltage, and C phase voltage here. If I have voltage and resistance, there will be A phase current, B phase current, and C phase current. Also, I can expect neutral current. Yeah, this is my point. Somewhere on the line, non-symmetry occurred. I'm taking kind of general case. Yeah. Since zero current is 1/3 of A phase current plus B phase current plus C phase current, you can check it from the start point, I can say what my neutral current is triple zero sequence current. Yeah? My current, my rules. Since here flows A, B, C, sum of them. And neutral, you can check from starting point of Fortescue transform. I will get this. Now, what I will do? I will write a system of equation. A phase voltage, what can I write? It will be A phase current multiplied by A phase resistance plus triple neutral resistance multiplied by zero sequence current. B phase voltage will be B phase current multiplied by B phase resistance plus triple neutral resistance is zero. And C phase current will be C phase voltage will be C phase current multiplied by C phase resistance plus triple neutral resistance and zero sequence current. I will convert it, knowing what sequence voltage effect, that will be 1/3, transform matrix, phase voltages. Here is tiny moment. I need to understand, or I need to choose a calculus phase. My model in sequence coordinates, which phase it corresponds? As I wrote it, it corresponds to A phase. I will perform a calculus on phase A. It is more preferable. Why? Because I will not do one additional supplementary work. I can omit and transfer angles between electrical machines, coordinate system DQ, and my coordinate system. Performing calculus on A phase simplifies work for me because Q axis of synchronous machines represented in DQ coordinates will correspond to A phase. I'm bit reducing my work. If needed, transform can be performed also for B and C phase. You can take this book in the library. It's also available in electronic form and read it. Usually A phase is used. thing is complex enough. So additional projection from the machine coordinates into calculus space coordinates isn't necessary. Okay, where I'm going? So I will get something like this. OA of direct sequence, OA of negative sequence, and zero sequence voltage, they are equal on all three phases, should be 1/3, 1A square, 1A square A, 1, multiplied by A phase voltage, B phase voltage, and C phase voltage. Here, again, A is a power of 2/3 or minus 1/2 plus your square root of 2 divided by half. Why I'm writing this? Because I need sequence voltages, 1/3 matrix of Kierkegaard, diagonal matrix of resistance, it A, Z, B, Z, C, plus neutral resistance matrix, 0, 0, multiplied by Kierkegaard, multiplied by sequence currents. Since phase current can be written as an inverse Fortescue transform of sequence currents, I can write following. Sequence voltages are 1/3 Fortescue matrix, diagonal matrix of resistance, inverse Fortescue matrix, plus triple neutral resistance matrix multiplied by sequence current. This gives me key element. It's an interconnect between sequence schematics or say any schematics, any real schematics can be represented in mass form as a kind of actuation system, starting from, let's say, what kind? From Kirchhoff actuations. Currents I and here, for example, Kirchhoff's equation system. First, Kirchhoff current law, Kirchhoff voltage law. Matrix nodes branched, matrix branch contours, resistance, branch currents, current sources, voltage sources, or EMFs. Any network has its mass representation mathematical. Sequence networks also. Any sequence network, direct, negative, zero sequence, can be represented as a equation system, connecting current sources and EMFs with its currents of voltage, if we speak of nodal voltage system. This one connects independent sequence systems in one. Totally, for three-phase network, we should have ability to interconnect, 6 objects. 3 equation systems for sequences. This equation system should, if we perform, for example, calculus for A phase, they should produce A phase values. They should produce values at the point of non-symmetry, at the point of fault. And something connecting them together, something what will interconnect. Direct sequence network, negative sequence network, and zero sequence network in one. So I will have 3 equation systems for each sequence network. One for each sequence network. Totally 3 equation systems. And this one interconnects them into one common system. It's an order condition. I can rewrite it in this form. A phase voltage, direct sequence. A phase voltage, negative sequence, zero sequence voltage equals to 1/3 1a square 1a square a 1 multiplied by ZA, ZB, ZC multiplied by 1 a square a1 a square 1 is correct. Plus triple 0 0 Z NATO multiplied by a direct sequence in a negative sequence I0. Here is border condition. PV. Please check correct matrix for in Fortescue transform inversion. 1, 1, 1, A square, A, 1, A square, 1. Please check. Okay. There is one moment. I can, if I perform a calculus on fold, I can really take any phase, A, B, and C. But there is one obstacle, or one moment. From the all possible folds, to analyze protection performance, I can take anyone. But it is more preferable to take one for which so-called complex substitution schematics can be created. The point is, what if I can substitute multiply. If this multiply can be substituted with real matrix, this means what I will get corresponding network what physically exists. Physically possible substitution network. For the case of Earth's fold, for the case of Earth's fold, it is preferable to analyze moment when equals to ZC. In such case, this term, the diagonal resistance matrix multiplied by inversion of Fortescue transform matrix, will produce a matrix with real elements what can be substituted, and this will yield a real physical network. Old timers used schematic like this with fault resistance from the A phase and infinite resistance in B and C. Its simplification, but since B phase and C phase currents are zero, very easy to obtain border conditions like A square I1 plus A negative sequence plus zero sequence equals to zero, and A direct sequence currents plus A square, this is square, negative sequence currents plus zero current equals to zero. This means what direct sequence current equals to negative sequence current and equals to zero, it's A phase. Also, A phase voltage equals to A phase resistance direct negative plus 0. It's for A phase, meaning triple direct sequence current of A phase. So, direct sequence voltage plus negative sequence voltage plus zero sequence voltage equals to triple A sequence resistance, A phase, direct sequence current. OA direct sequence equals to triple A phase resistance, direct sequence current of A phase minus negative sequence voltage plus zero sequence voltage. The longer you sleep, the better I eat. Yeah, so what I can draw? I can draw an equivalent schematics for ideal earth fault. For ideal earth fault, I have ideal earth fault in A phase. For such ideal earth fault, my schematics will be ground point, equivalent resistance of the direct sequence, equivalent, guys, equivalent resistance of direct sequence, connection terminal for direct sequence. This is ground point for direct sequence. Next, common terminal for negative sequence. Equivalent resistance for the negative sequence and connection terminal for negative sequence. Here, common point for negative sequence. When you assemble, when you design a negative sequence network, this will be common wire for your negative sequence. And again, common wire for zero sequence. Equivalent resistance for zero sequence and connection point for the zero sequence. Interconnection. This goes here, this goes here, and triple resistance at fault place. In case you have, for example, free phase network and an earth fault with transient resistance RF, this is earth fault. this one will become triple fault resistance. It's your calculus model. Free interconnected network. First you conduct schematics for direct sequence, maybe. It's like a symmetrical load regime. Negative sequence, like generator with opposite phase sequence is attached at the fault place. And special zero sequence. This is calculus model for single phase fault. When we speak on ground fault protection or earth fault protection, these schematics will be paramount. Without this part, successful analysis of earth fault protection is simple futile. Elusive. It's illusion what analysis can be performed without direct and deep knowledge of zero sequence network. Yeah. What I need? Also, same technique can be applied to line-to-line fault. Same idea. I need symmetry. B phase, C phase, but they should be equal. With C phase, A phase current 0, here will flow B phase current, and here I'm expecting C phase current. One second, I will service my instrument. phase current 0 and direct plus negative plus 0 is 0 because I don't have a ground connection. Earth fault protection should be immune to face-to-face fault. E0 is 0, no ground connection. So, direct sequence current equals to minus negative sequence current. Here is convenient to write for border condition. So A squared, A phase current of direct sequence plus A for negative sequence A direct sequence plus A squared A negative sequence equals to me minus B phase current. Whoop. So, what does this mean? B phase voltage minus C phase voltage equals to 0. Meaning was direct sequence voltage equals to negative sequence voltage. And I can draw nice schematics. Unified, maybe better say united substitution schematics for BC fault. Equivalent EMF of direct sequence, equivalent resistance of direct sequence, attachment point of direct sequence. This is common wire for direct sequence, it's grounded. On, how to say, mirrored, I will have common wire for negative sequence and they are interconnected. Here flows direct sequence current of A phase. And one, I will mark it current. I'm considering BC fault, but this schematics corresponds to A phase. Here will be my B. It's equal. Attachment terminal of negative sequence, equivalent resistance of negative sequence, and this nice bus is nothing else than a common wire for negative sequence. Huge common wire. This is schematics for face-to-face fault. There is a more general schematic, or more general schematic can be derived, so-called asymmetric star. Easy for calculus. Most general solution should be done in iterative form using large equation I wrote first. These are particular cases, how to say, with reduced computation burden. And one of such easy to perform calculus, known for easiness, is an asymmetric ZB. ZC, but it is important. ZB should be equal to ZC. There should be a BC symmetry. For such case, if they are equal, it is possible to conduct a common network for non-symmetric star. This common network is easy to calculate. So case network representing this asymmetric star. Ground point. This is common wire for direct sequence. Equivalent AMF of direct sequence and equivalent resistance of direct sequence. Attachment point for direct sequence. Equivalent resistance of negative sequence and attachment point for negative sequence. And this is common bus for negative. Here will be equivalent resistance for the zero sequence and attachment point for zero sequence. Common wire for zero sequence. This all should be connected together, and here goes B phase, again B phase equivalence, triple neutral resistance, and an equalizer, one third of ZA minus ZB. Equalizer resistance. Here it is. Here is schematics for the non-symmetric star. It's more general schematics. In general case, use first iteration. It should be done inside sequent or iterative solution. This can be solved as one network. Open course computer application, and you can solve this network. More. Special kind of tasks are line interruption tasks. Special kind of protection are line interruption protection, because non-symmetric regime or non-symmetrical mode is dangerous for asynchronous machines. It's called overheating. Especially on expensive machines. One of the my first scientific works was protection for oil pumps. They are nice. Surface installed oil pumps. Actually, pump itself is deep in the well, and it's connected by this long shaft or rod, call it. But there also are models where pump is cylindrical one, it's has a factor of long cylinder and it's put here, down in well. They are very expensive and and not repairable. If the surface mounted machine can be repaired, we are unlucky. These deep well, not dry but deep well pumps are not repairable. So good protection for them, it's a matter of serious money. Special kind craft design, special protections, able to detect non-symmetry and disconnect this very expensive equipment timer. По симметрическом компоненте. Symmetrical komponentu metode vajadzīga, lai rēķinātu asimetrisks režīms. Tūlīt tas atradēm paraugumus atsevišķi. Yeah. So, what I'm about? I have three resistance connected seriously. Let's say general. So here was A phase current, B phase current, and C phase current. I have resistance A, B, C, some resistance. And I have voltage drop on each resistance. Here is idea. Longitude non-symmetry. Different resistance in phase. Actually, I'm interested in easier case when one wire is interrupted or two wires are interrupted. What is really painful, if you disconnect on MV network one wire, there still will be a voltage on all side network. And no one starts a buzzer until equipment starts to burn. So what can I write? Voltage drop in A phase. It is A phase current multiplied by A phase resistance. B phase voltage drop. B phase current multiplied by B phase resistance, and C phase voltage drop. Yeah, it's easy. What I need? I need a calculus, something for calculus. I can convert this into symmetrical transformer. Yeah? So, in terms of symmetrical components, I will get 1/3 Fortescue transform matrix and this one is delta U in phase coordinates. This is absolutely clear. Absolutely clear. And if this is clear, I can write delta U in sequence as 1/3 Kierkegaard matrix diagonal matrix of resistance inverse matrix of Fortescue transform current in sequence form. This, it gives me what? Complex, they all are complex. What this gives me? Interconnection between sequence current and sequence voltage. I'm rewriting in coordinates will give me, so delta U A phase direct sequence, delta U voltage drop A phase negative sequence, zero sequence equals to 1/3. Next, 1A square, 1A square, A, 1, 1, 1. It's a transform matrix of Fortescue multiplied by ZA, ZB, ZC, multiplied by 1, 1, 1, A square, A, 1, A square, 1, multiplied by A phase current direct sequence, A phase negative sequence, zero sequence current. Direct sequence. Here it is. This form is common or universal or global. It works for any. Usually, derived, more simplified form are used. Usually, we will take two, how to say, limit forms except we are digging very deep. Once I dig real deep, I searched for non-sensitivity area of protection. It was nice calculus. It took only 2 hours for one sample. I made a mistake, but it was nice. You start machine and go. For most common purpose, 2 cases will work. One, when you have resistance in A phase and complete infinity in, this is A, this is B, this is C. So complete infinity in B and C, only one phase is connected. One case. And another case, you have zero resistance in B and C. It can be up to infinity. It's one phase interruption, or there is a quite unpleasant thing. Sometimes you need to perform a technical expertise on faulted equipment. And one of the things, badly performed assembly or rusted somewhere, when one of the terminals burns out to normal, one black, rust and burn. in case one of the terminal burned, you will have this condition where here something approximate of this damaged terminal. It's very unpleasant because actually company should pay damage for non-servicing network properly. But company don't like to pay, and you will be one who's to blame. Why company pay? I don't know. Do I have a burned? No, this one okay, this one also in good condition. It's on the first floor. Okay, nothing special. At the first floor museum you can see burned fuse. Yeah. For the first case, you for this one, two-phase disconnection, only one phase remained. Good substitution network is known. Ground, common wire for direct sequence, common wire for negative sequence, and common wire for ground sequence. Equivalent EMF of direct sequence for the left side and equivalent resistance for the direct sequence for the left side. M1 and okay. Let's simple M1. This will be in this case K1. Equivalent resistance for the right side of the network. For such fault, you will need to separate your network into left and right and perform an equivalent for the left and right side. Left negative sequence equivalent resistance for the right side and zero sequence for the left side and equivalent resistance for the right side. Yeah. Now interconnection. This goes here. This goes here. And this goes here. Here it is. Here is network. You need to deal with. Usually you will also need this voltage. Okay, if we will be able to speak about motor protections. So this network is for interruption of two phase. Single phase operation of three phase network. for the case you have one phase interrupted, another network will do. I don't know, write it somewhere. Okay. Believe me, you will not find this information anywhere. Really. The books will be on your disposal. Do not contain this. Something close, you will need to search for Atabekov's book. It was translated in English somewhere at the end of 1950. Because later nothing happened. Atabekov died suddenly. No modern book contains this information. Yeah. I did it by myself. You will see something like use our Genial program and maybe you will be able to so here is case. This one is usable. It's not usable, but this one is used more often. Left, that one, right? These are equivalent resistance. E1 left, A1 right. Equivalent EMF. What is equivalent EMF? Eh? What's mean equivalent? What Thevenin theorem tells us? Thevenin theorem. Ooh! Thevenin's theorem or active two-pole theorem. What Thevenin theorems tell us? What any network what has two output terminals can be substituted with equivalent EMF equals to non-load voltage and the equivalent internal resistance equals to equivalent EMF divided by short circuit current. You should know Thevenin theorem. So these are Thevenin equivalents. These are equivalents in terms of Thevenin theorem. M1, M2, K2, K1, Thevenin's theorem. Zero R, zero left, and 0 and 2 and 1 ground point. And this one is 1/3 ZA. This is your fault resistance. Here is substitution network for Z. For what? For the case you have resistance in one phase. This one works in case you need to perform a calculus for the fault on the MV side. This will work. But that's not all. I'm only shown what? General networks. Next time I will waste time on you. I'm wasting my time. Yeah, I'm wasting it. We need this small, nice network. Now I'm just writing equivalence, but what equivalence of what? We need to analyze a non-symmetrical fault. We need to conduct sequence network. Our first target will be zero sequence network, really. But we need to be able to conduct them all. When we will start to speak on distance protection, we will need all. That means what I have to spend one more lecture on components, and there is one more very tricky moment when many people failed, really many failed. It's a transformer. What happens? You have connection, high voltage network, distribution network, and distribution network, customer, 0.4 kilos. On both, you will have transformers, star delta or delta star. These transformers are significant. You cannot ignore them. They're changing a lot. But for today,